Okay, so for this question, I'm going to do it a little bit differently. I'm just going to talk through their working. So the first thing that we want to talk about when we're looking at the volumes of revolutions is we want to talk about the formula. Where does it come from? Why does it work? So the first thing we're going to talk about is this picture here, which is called an annulus. So an annulus is this blue exterior part that can be made up of the big circle, or the blue one, minus the little one, which is the yellow one. Now, the formula for the annulus looks like this, where it's pi times the radius squared minus pi times the radius of the smaller one squared. So, looking at our formula that we've got over here, you can see that they're quite similar. I've got pi, I've got a radius squared, and I've got another radius squared. So all we're really doing is, instead of having a fixed radius in 2 dimensions, we've got a function for the radius in 3 dimensions. Now, part A asks us to rotate it around the x-axis, which means I want you to think about projecting this the whole way around the x-axis. Now, more graphically, what that's going to look like is, if you picture like a men's wedding band, it's going to look like that, but on its side. I don't know how to flip that picture around. That's staying like it is. But it'll be like that, but on its side. So that's the volume that we're calculating, that kind of shape in 3 dimensions. So to calculate that, all we've done is we've put those functions that we were given originally, y equals this and y equals that, into our area between curves. So for our area between curves, it's the top function minus the lower one. So this one here, between A and B, fx is the top function, so fx goes first. For us, our function of y, or 9 minus x squared, is on top, so that'll be the one that goes first, which is why here that function goes first. So this one here, this here is on top because that's on top there. Now, the next one that we're going to look at is this 25. Now, just like here, you minus the one that's on the lower. So that is the lower fraction, which is why it's getting subtracted. Now, that was 5 squared, but they've just simplified it straight down into being 25 there. So really, it's the top one squared minus the bottom one squared, because that's getting us the area of the annulus in 3 dimensions. Now, the next thing that I want to talk about is your lower and your upper bounds. So you can see here that I've got one point of interception at -2 and one up here at +2. So that's why here it starts at -2 and +2. And that matches up with our formula that we're given for this kind of equation. Now, over here, they've just randomly got this 2 out the front. Now, the reason why they've changed that to a 2 is they've said, well, this thing's going to be symmetrical. So I can put a 2 out the front and I can integrate between 0 and +2 instead of between -2 and 0. Now, this actually has no effect at all. Your other option is, in your calculator, you can do pi multiplied by 2 -2 9 minus x squared minus 5 squared bracket with respect to x. It gives you exactly the same answer. This is something that you need to know how to do tech-free though. So make sure that you can do this without a calculator. I think that that's the reason why they've opted to halve it, so that they can try and make the algebra later a little bit easier, because putting 0 in is a lot easier than trying to put 2 in and then trying to put -2s in, and then you get calculation errors. But if you choose to do it between 2 and -2, get the same answer here, no problem. Now, the next one that we're going to talk about is what happens if we rotate about the y-axis. So, rotating around the y-axis means that it's going to spin in this direction to create our 3-dimensional object. So it's going to look like this elliptical cone down here. So, in order to do that, what we have to do is apply our formula. Now, again, we would be looking at what's on the y-axis. So, on our y-axis up here, you can see that it goes between like 5 all the way up to like 9, and it's rotating around there. So I'd solve to find those intercept points to spin it around. But really, that's the hardest thing that you have to do here. When I rearrange this equation to get, like I rearrange the, do I rearrange? I'm going to rearrange it to get x equals for both of them, which is why down here this equation changes. So before we had y was equal to this. We had y equals 9 minus x squared. And now in here I need to put it in as a function of y. So y needs to be in the equation, which means that I'm going to be substituting in y, take the 9 across, divide it all by -1, and then square root that answer. And that's going to give me x. Now, when I square that, because I'm going to put that into my equation in this step here, and I'll end up with y minus y plus 9, all square rooted. And then when I square that, this will knock this out. So I'll be left with just 9 minus y. So that's how they get between those two steps. To find these, all I need to do is solve for my, when x equals 0, what is y in both equations. So when x equals 0, y equals 9. And in the other one, when x equals 0, y is still 5. So that's how I get my lower and my upper bound. I think that's probably all the things that you could possibly get incorrect in that question. So good luck.